Welcome back, everyone. So today I want to go ahead and go over um, AC versus DC. Okay, so up till now, our voltage has been steady state. Our voltage has just been a constant voltage, a fixed value that stays the same throughout the whole running of our circuits. And that is actually kind of boring. So, what comes into our houses is alternating current. So, let's go ahead and let's break this down into alternating current versus direct current. And this is that infamous battle between Nikola Tesla and Thomas Edison on what was going to power the country. And ultimately, Tesla won out with AC for a few practical reasons that I could get into later if anyone is interested. But let's go ahead, and direct current is what we've been dealing with this whole time. That's that constant voltage source, always gives us 10 volts or 12 volts or 5 volts, but it stays the same the whole time. So when you go ahead and looked at direct current, we would have like a constant voltage source applied to something that's going to use the energy or dissipate some power. In this case, we're just going to have a resistor over here. And so we know that we're going to just get a constant current running through this with some value I dictated by the voltage source divided by the resistance in accordance with Ohm's law. And if you go ahead and graph this, now that we're going to have some changing voltages, if you want to look at a changing voltage, you're going to have to look at a graph. So let's go ahead and put up the boring graph of what this looks like. We're going to put our x-axis at 0, and we're going to have a voltage V sub S, whatever that is. If that's 10 volts, that's going to be at 10 volts, and time will be going in a positive direction to the right. So we're looking at time with respect to voltage, and we get this constant DC. We get this constant line of direct current in a circuit like this. Now, if we're going to go ahead and look at AC, well, now our voltage source is going to change a little bit. We're going to denote it with a circle. So let me go ahead and write alternating current. Let's give it a AC voltage source. Typically, we'll draw that as a circle with a little sine wave denoted in the center of it. And let's go ahead and apply this to some resistance. Let's say our magnitude over here for our AC voltage source is, we'll call it V sub S as well for now. And let's go ahead and let's center everything at 0. Sorry, somebody's microphone is coming through. And now let's go ahead and let's see. I can't actually turn that off, unfortunately. Ah, I just got it. Okay. Cool. And so let's go ahead and let's look at this AC voltage source. It's going to go up. And it's going to go back down. And it's going to go back up. It's going to continue this on forever. And now, if you notice, half of the time, we're going to be applying a positive voltage to this. In other words, half of the time... Yes. Oh, sorry about that. Let me move my big head out of the way. There we go. Perfect. Okay. And so half of the time we have this positive voltage being applied over here. So you can quite literally think about it as half of the time we have positive up here and minus over here, and we're causing the current to go in this direction. Now that's going to happen anytime our applied voltage is positive, which occurs anytime we're above the x-axis over here, since we set that at 0. Now, we do have a name for this. This is known as the positive alternation. So let's throw some terms out here. This is the positive alternation. And then the other half of the time, when the applied voltage is below that x-axis, our polarity has now flipped. We're now positive on the bottom, minus on the top, and current is now actually going upwards. And during this time, we refer to this as the negative alternation. Okay, so we have the positive alternation and the negative alternation. This ends up being quite useful once we start analyzing things, because many circuits will actually behave differently when the voltage is positive versus when the voltage is negative. There are some clever things that we can actually do with this alternating current over here. But one of the things I want to talk about now is how do we quantify the magnitude of this. Now we could go ahead and say, well, V sub s, it goes up to V sub s and goes down to minus V sub s. That is one way that we can go ahead and quantify the magnitude of this AC voltage that we would use and apply in our circuit. So let's go over. There's actually a few different ways that we can quantify the magnitude. And the three ways that we can, the first would be specifying it as a peak voltage. We'll denote this with a V sub peak. Okay, for peak voltage. So these are the three ways to describe the magnitude. Three ways to quantify the magnitude. Okay, and each one of these ways is useful in different circumstances. Okay, so the first was the peak voltage. The peak voltage would be the highest voltage that the AC actually reaches. Okay, in fact, that's how we described it over here. V sub s, if this was 10 volts, it means we go up to 10 volts. Okay, so that's definitely one way we could do it, and we would refer to that as the peak voltage. Okay, another way that we could go ahead and specify it is the peak to peak voltage. And if a value is given in this, we would say it's V peak. Sometimes they put this hyphen between the two, peak, or sometimes they just say VPP. Or they'll leave the hyphen out and they'll just say V peak to peak. Okay. They all mean the same thing. They're the peak to peak voltage. So in this instance over here, where our V sub S is 10 volts, this is actually 10 volts peak. And if it goes up to 10 volts, then it goes to say that it also goes down to minus 10 volts. And so if you want to describe this same exact magnitude but specify it as a peak to peak voltage, then you would go ahead and say 20 volts peak to peak. So this 10 volts peak is the same. It is equivalent. It is identical to saying 20 volts peak to peak. Okay, so we're just saying the difference between the highest and the lowest as the magnitude. Okay, so that's what we would be implying when we get to peak to peak. Okay, the third way, which actually ends up being very useful in certain circumstances, is the root mean square. The root mean square, typically people would write VRMS. Okay, so we know peak voltage and we know peak to peak voltage. What's the idea here behind this root mean square? Well, I think the best example that I can give is probably what comes out of our electrical outlets in our house, in school, wherever it is that we are, at least in the US. What is the magnitude of our electrical outlets? What did someone volunteer? Sorry, what's that?
Because there's that French sugary maple syrup that I like the flavor. But I grabbed for the honey.
Oh, yeah, somebody else is unmuted and talking about maple syrup. Okay, somebody said 120. Okay, so let me go ahead and let me draw what comes out of our electrical outlets. Okay, so this is the voltage that's coming out of our electrical outlets. And it turns out it goes up to 170 volts and similarly goes down to minus 170 volts. Okay, what's up with 120? Why is it 120? Where is 120 on here? What's going on? Okay, why on earth are we going to be talking about the magnitude of this AC voltage as being somewhere around here. Why? Whoa, that's weird. Okay. But it goes up to 170 volts. Okay. Here's the problem with peak voltage and peak to peak voltage. I really can't calculate much based off of the peak voltage. Okay. Because the peak voltage, it's only this voltage at this one moment in time. Similarly with the peak to peak voltage, it's only 340 volts peak to peak. So let's go ahead and get this out of the way. This is 170 volts peak, which is equal to 340 volts peak to peak. And as somebody said, what comes out of our outlet is 120 volts RMS. Okay, so here's the motivation for RMS. I would like to specify this as an average voltage. We're only at the peaks for a moment in time. The rest of the time we're somewhere else. However, it'd be nice if I could quantify my AC voltage as an average voltage. So RMS, or root mean square, gives us a method to talk about our voltage as an average voltage. But we can't go straight to an average voltage because what's the average of a sine wave? What's the average voltage? Yeah, that sucks. That's useless. If I apply this to a resistor, don't I get power dissipated from that resistor? Don't I have current running through it? So there's really nothing that I can do with an average of a sine wave as far as numerically and mathematically. It's 0 volts. It's like, okay, well, no. It's doing something. It's not 0. Okay, so this is the motivation for the root mean square. In fact, let's go ahead and let's take these words and write them out. So root, as in square root, mean, as in the average, and square, as in taking something raised to the 2. Okay, so it's gonna involve these operations over here. So if we want to quantify an average voltage for our AC, let's start with something we're probably pretty comfortable with, the peak voltage, the highest voltage that we reach. I'll go ahead and call that the peak voltage, the highest voltage that we get. Now, what's messing with us is we can't take the average because this is, well, dipping down negative just as much as it's going positive. So is there a way that we can take all of our voltages and actually just turn them all positive? Yeah, I can go ahead and take the square of something. If I take the square of something, I get rid of the minus signs. Okay, so now all of my below the x-axis negative values have now become have become positive. Okay, so now we have v peak squared. Okay, now we can actually take the average of this. If we take the average of this, we now have a value that represents the average voltage. However, it's the average of what was squared. So if we want to undo this square, now that we actually have a true value that is indicative of the average of this voltage, but it was the average of it squared, we can undo the square by just taking the square root. Well, what does that end up giving us? Well, once you go ahead and undo the square, we now have an average voltage indicative of the magnitude. We have VRMS, or the root mean square of our voltage, is equal to the square root of the average, or the mean, of our peak voltage squared. And this very commonly gets abbreviated to VRMS is equal to 1 over root 2 times V peak, or VRMS equals 0.707 times our peak voltage. And memorize this one. So now if we go back over to, and I see that somebody already typed it in chat, awesome. For our peak voltage of 170, one over root 2 of 170 volts equals 120 volts RMS. So if I pull up my calculator over here and do 0.707 times 170 volts peak, I get 120.19. Okay, so that's where we get the 120 volts RMS. Now, there's a good reason for doing this. And it comes down to the definition of RMS voltage. RMS voltage is the value of AC voltage or current. So when we take when we're looking at VRMS, this could just as easily be IRMS if you're talking about the root mean square of the current, and it would just be the peak current times 0.707 gives you IRMS. It's the value of AC voltage or current which produces the same heating effect and if we're talking about heat being dissipated by a resistor, you're talking about the power being dissipated by the resistor. As an equal value of DC voltage. In short, we get back Ohm's law. So the same load resistor in both of these circuits, except one of them has a DC voltage source and the other one has an AC voltage source. And this one over here we're going to say is 10 volts. Where this one over here we will say it's 10 volts RMS. And the power dissipated, in fact, let me go ahead and make the distinction over here, RL1 and RL2. Power dissipated by the DC version is equivalent and the same as the power dissipated by the AC version. So this is what's useful about an RMS voltage. It produces the same heating effect, meaning power dissipated as an equal value of DC voltage. 10 volts RMS is functionally equivalent and identical as far as the power is concerned when comparing the AC version of this circuit to the DC version of this circuit. Okay, so pretty cool. So now we can go ahead and we can get back Ohm's law and our power equations for AC circuits. We just have to write it a little differently. We would say V RMS is equal to I RMS times R, whatever our resistance is. And now P average is equal to I RMS times V RMS. Yay. we now have a way to quantify the AC voltages. Okay, do I have any questions about this before we continue on? If you want me to numerically go through this one, I'll go ahead and do that here. IRMS is equal to, well, it's just VRMS, which we already have specified as 10 volts, divided by R, which is 10 ohms. This means we have 1 amp of RMS. And now you can go ahead and take that times 10 volts RMS, and your average power is going to be equal to 10 watts. I guess we could do that. Squeezing it in over here. 10 watts. Okay, power is never said to be in terms of RMS. It's not root mean square power. It's average power. Okay, so yeah, so RMS, great way to get our equations back. Okay. Now, one of the nice things about having AC is that it's changing for us. In other words, it's already doing some work for us. We can actually leverage this to our advantage. If we have AC coming into the wall, it's already alternating, and there's a really nifty component that can make use of this. Now, we don't have a new lab today to start, so I'm going to go a little over on time. And we're going to talk about some robots in disguise. Sorry, I meant Transformers. We're talking about Transformers. Okay. Now, Transformers, this is probably the reason why AC won. Actually, I can tell you for sure. This is the reason why Nikola Tesla ended up winning in the AC versus DC argument. Because transformers are very simple device that give us a very powerful thing that we can do with AC voltages. We can make a voltage higher, or we can make a voltage lower. Okay, keyword AC. Transformers only work with AC. DC will not do anything when connected to a transformer. So let's go ahead and let's draw up the schematic symbol for a transformer. Okay, now we have two sides. We have two terminals on one side, we have two terminals on the other side. This side that we're going to consider to be the input, and I'm going to always draw this from left to right, where this is our input, this is our output. This is referred to as the primary. And the secondary is referred to as the secondary. And from the schematic symbol, you can see a couple of things. Read into this for a minute. On one side, it looks like we have an inductor. On the secondary side, on this other side, it looks like we also have an inductor. And they're not electrically connected to each other, okay? But they are physically close to each other. And if they're physically close to each other, they're going to share a magnetic field. Okay, remember about inductors. Inductors store energy as a magnetic field. So in essence, what I have here are two inductors that are sharing the same magnetic field. When one changes the magnetic field, that magnetic field is going to influence the other one. In fact, let's go ahead, let's draw this physically as to what this would look like. Okay, physically, I'm going to go ahead and draw what we would call the core. Okay, now the core is just a chunk of ferrous material, something that can concentrate some magnetic field lines, something that is essentially magnetic. And when we talked about inductors, we did talk about a couple of different cores. You could have an air core. In other words, you can have no core. You're still going to have a shared magnetic field if these two inductors are physically close to each other. So if I took two inductors, here's an inductor, and here's an inductor, and we know if we pass current through one of these inductors, it's going to build up a magnetic field around it. And if I just put it next to the other one, this magnetic field will influence this inductor, okay? In other words, we get a changing magnetic field, and this changing magnetic field causes current to flow out of this one. Okay, so we have some kind of shared core, and then we're going to create our inductors around this core. We have a primary, and we have a secondary. Now, we do call this the primary windings. Just as though we were creating an inductor, how many turns do we have? Those are our windings, because you're winding wire around something. Now, I can go ahead and show you a proper transformer. Here's a small transformer. They do get much larger. Here's a larger one. If you notice over here, I have primary on one side and I have secondaries on the other side. Over here, this is a smaller transformer. This one's designed more for small signals, but nevertheless, it's the same idea. I have windings around a core, and I have another set. They're electrically isolated. There are no electrical connections between these two inductors. There's no electrical connections between these two sets of coils. They are only interacting with each other through the shared magnetic field that's concentrated inside of this core. Now, as we apply AC to this input, half of the time my magnetic field lines are going in this direction, and the other half of the time my magnetic field lines are going in the opposite direction. Well, what happens if I have a changing magnetic field in the presence of a coil of wire? I'm going to get an AC voltage out of this. And in fact, this might be a fun time for me to go ahead and fire up our oscilloscope and function generator, and we will see the AC going into a transformer and the AC coming out of a transformer. So let's go ahead and let's take this transformer here. In fact, if you don't mind, I'm going to flip this upside down so it stays in place a little better. And I am going to turn on an instrument called an oscilloscope. Now, an oscilloscope allows me to view a changing voltage with respect to time. And what I'm going to first do is I'm going to take my oscilloscope probe. So this is going into my measurement instrument. And this is coming out from my function generator. It's going to behave like an AC voltage source. Now, voltage is always measured between 2 points. So as well as measuring the positive side of my voltage source, my AC voltage source, I'm also going to have to measure the minus side of my AC voltage source. So I don't have a transformer hooked up just yet. All I'm going to do is look at what's coming out of my AC voltage source. And for that, I'm going to need to fire up. Where is it? There we go. Okay, so right now I'm just taking a voltage measurement of my AC voltage source. If you notice, if I disconnect, so down here in the lower left, I'm going to go ahead and disconnect my oscilloscope, and you're going to notice my waveform disappears. Okay? And then as soon as I connect it back up, I get my AC voltage source back. So absolutely, I'm measuring the output of my function generator. My function generator is just providing us an AC voltage source to look at this thing. Now I'm going to zoom in a bit along the time axis, and maybe I'll zoom in also on the vertical axis, and let's see what the frequency of this is. So frequency is just how many cycles per second. Right now this is 10 kilohertz. If you look at the lower right hand side of my oscilloscope, you'll see that I have 10 kilohertz. That means 10,000 cycles per second. Each cycle is measured from where it starts to where it repeats. So if I look along the x-axis here, let's say that one cycle starts here. Well, it ends right over here. So I'm getting 10,000 of these per second. Now, what comes out of our outlets is not 10,000 cycles per second. It's actually 60 cycles per second, or 60 hertz. So what I'm going to do is I am going to crank down the frequency on my function generator in order to match what's coming out of the wall. Okay, so I'm now at 60 hertz. I'm at 60 cycles per second. However, if you notice, my oscilloscope is quite a bit zoomed out. If I go ahead and change the scaling, you can see I'm getting back my, okay, there we go. And now I can see about, let's see, about 3 cycles on my screen. 1 cycle here to here, 2 cycles from here to here, and 3 cycles from here to here. Okay, now let's go ahead and what I'm going to do is actually go back up to 1 kilohertz for the sake of this example. Okay, and you can see my frequency measurement from the oscilloscope is down here and to the right. And what I'm going to do is I'm going to take my AC voltage source and I'm going to connect it to the input of my transformer. I'm going to take the output and I'm going to measure the output like this. Okay. Check it out. It's exactly what I said. I'm getting AC out of this. Now let me go ahead and start up another probe. Oh, I might not be able to do this. Yeah, I can't. Okay. Unless I hook up another probe, I could. Yeah, sure. Actually, that's going to take too long. Okay, never mind. If you look at the output is a sine wave. And the input is our AC sine wave. Okay? So AC is getting through this transformer, no problem. However, DC will not get through this transformer. Okay, so AC can get through this no problem because the AC is, you can think of this as a generator inducing this alternating current on the output over here. But DC, when I apply a constant voltage to this inductor on the primary side, the magnetic field gets as big as it can and then it just stays there. It saturates. It doesn't get any bigger or smaller. And so the electrons will initially wiggle in one direction in this coil, but they aren't going to move in the other, so it just gets stuck. And so you don't get any DC coming out of it. And let me show that over here. And I bet the easiest way for me to show this is with a 9-volt battery applied to our transformer. If I take a 9-volt battery and hook it up to the input, we're going to look at the output on the scope. So I'm going to take my black mini grabber clip over here, and I'm going to clip that to the minus side. I'm going to take the yellow one, and that's going to be connected to our positive 9 volts. And I'm going to take this to the input of this transformer. And now let's see what the output is. Nothing. Oh, wait. Sorry. Nothing. Yeah, we have no voltage coming out of this. Okay, so a transformer will allow only so badly. So the inside of the transformer is creating a rotating magnetic field, right? Not with DC applied to it. So once that magnetic field builds up, if you go from a 0 volts to 9 volts, then yes, when I initially attached the battery, there was a changing magnetic field, but eventually that magnetic field stopped changing. And the moment we get no change on our magnetic field, we get nothing coming out of the transformer. But inside of the transformer with AC applied to it, absolutely you are getting a rotating magnetic field, an alternating rotating magnetic field. And in fact, do I have my compass laying around? I could show that. All right, here's a here's a compass. Let me get... Come on, coil. Where are you? Come on. Where are you? Oh. Here you are. So if I set up my inductor, nothing more than a coil of wire, and I set it up to my magnet, and let's go ahead and apply some AC over here. See that? Okay, so I'm applying right now a 1 hertz signal to this. And you can see that because the magnetic field is changing, absolutely, an inductor is nothing more than just a coil of wire. And it does look like this compass is wobbling at a rate of 1 hertz. If I go ahead and step that up to 2 hertz, let's get a little faster. And if I change the amplitude, I should get a little more weeble to my wobble. Because as I increase the amplitude of the AC voltage to my inductor, I'm getting a stronger magnetic field. So I expect to see my compass go a bit further. And yeah, I'm comfortable right there. I could go up to 10 volts, wouldn't bother me. Okay. But if I go ahead and just apply straight DC to this, yeah, my magnet, my compass just gets stuck in one direction. And so the electrons initially get a push, but that's it. I don't get anything coming through it. I just get a one-time push and that's it. Is that good enough of a demonstration, or anybody else want me to try something else? That's good for me. Perfect. Okay. Well, let me go ahead and kill my oscilloscope. Okay, so you've now learned the most important thing about a transformer. It works for AC, it doesn't work for DC. And in fact, given how simple, and somebody said, wait, so you could just make an inductor with just a coil of wire? Yeah, so can you make just a transformer with just coils of wire? Absolutely. These are very simple devices. And they work because essentially we have this alternating current that's applying, doing some work for us. And that's really the reason why Tesla won. Because if you want to do the same thing with DC, it required a lot of technology that did not exist around that time. And so ultimately, because of the simplicity in how a transformer is constructed, it was a no-brainer. Once you needed to start doing power distribution and increase and decrease voltages, then you really kind of a transformer does a lot for you with a very simple construction. Yeah, so let's get on to how a transformer changes the voltage. I just wanted to make sure to spend some time on, on transformers need AC in order to operate. So now let's go ahead and let's get into how does a voltage change. Okay, for that, we're going to get into the turns ratio. And I'm going to use the physical representation of a transformer for this. Now, if we're making a coil, we have some number of turns of wire around this primary side. And similarly, on my secondary side, I'm also going to have a number of turns. And let's go ahead and let's say this side has 10 turns, and this side has 10 turns. And we can go ahead and quantify the number of turns on the primary as being n sub p. And we can quantify the number of turns on the secondary side as being n sub s. Now the turns ratio is actually going to give us the voltage ratio between the primary and the secondary. The turns ratio, TR, is equal to the number of turns on the primary divided by the number of the turns on the secondary. In this case, 10 divided by 10. However, the more proper way of writing this is 1 to 1. It's the ratio of turns on the primary versus the turns on the secondary. Since these both have the same number of turns, 10 on this side, 10 on this side, we can just call this a 1 to 1 transformer. Or more properly written this way. Now let's go ahead and let's set up a little example with a 1 to 1 transformer. This is all you're going to see on a schematic. It doesn't matter if I have 10 turns in this side and 10 turns on this side, or if I have 100 turns on this side and 100 turns on this side. Either way, I have the same number of turns on the primary as I have on the secondary, and vice versa. It's a 1-to-1 transformer. Now, the reason we care about this is because this ratio is going to determine what the voltage on the output is compared to the input. Now, we can go ahead and now say the number of turns on the primary divided by the number of turns on the secondary is equal to the voltage on the primary divided by the voltage on the secondary. In this case, because I have a 1-to-1, if I go ahead and apply ten volts peak well, the number of turns on the primary versus the secondary is just 1-to-1. The voltage on the primary is 10 volts peak. Very important to maintain your units as far as what type of voltage are we specifying. Peak to peak, RMS, or just peak voltage. If I'm talking about a peak voltage, the easiest is for me to just keep it the same. Voltage on the primary is 10 volts peak. Well, what's the voltage on the secondary equal? Well, just cross multiply. 10 volts peak times 1 is 10, divided by 1 gives me 10. Now, this was a very simple case. This was a 1-to-1 transformer. In fact, this is the same type of transformer. This is a 1-to-1 transformer. That's why you did not see any magnitude change when I probed the input versus the output. It was a 1-to-1 transformer. Now, we can go ahead and break this up into two different types of transformers. Step up and step down transformers. In other words, I should probably write it out this way. V on the primary is less than V on the secondary. In other words, you're going to get a larger secondary voltage. Or in the case of a step-down transformer, voltage on the primary is larger than the voltage on the secondary. Or in other words, we're creating a voltage that's lower on the output. So let's go ahead and let's look at a step up transformer. Let's go ahead and say we have 4 times the number of turns on the secondary than the primary. In other words, let's say we have a 1 to 4. Okay, so if this side has, say, 10 turns, this side's going to have 40 turns. Or if this side has 100 turns, this side will have 400 turns. The number of turns doesn't matter. The only thing that matters is the ratio between the two. Yeah, I can show you a variable transformer in a little bit. And you can take a step down transformer and flip it and call it a step up transformer. You could do that, yeah. Okay, but let's just say we have 4 times the number of turns on the secondary than the primary, and let's apply what's coming out of the wall. So let's say it's 120 volts RMS. Okay, and now the question's going to be, well, what's the voltage coming out of this? This is an AC voltage. Let's keep our units the same. Since I specified this as 120 volts RMS, well, what's coming out of this? Well, we can go ahead and set up our ratio just like we did for the other one. We can say NP over NS equals VP over VS. And so I can say the number of turns on the primary is 1, number of turns on the secondary is 4, equals the voltage on the primary, which is 120 volts RMS. And then I can say what's V sub S. And then I can go ahead and say, well, 120 volts times 4 gives me 480, and divide that by 1, and I get 480 volts. Okay, this is not enough. I need to specify what kind of voltage this is. Since I entered it in as RMS, V sub S is going to be in terms of RMS as well. Now, I could also just intuitively look at this and go, well, it's a 1 to 4 transformer. Hence, my output has 4 times the number of turns as the input. Therefore, whatever I have applied to the input times 4 gives me my output. That's how I tend to do it. I don't generally write this out. I just look at it. And if I see that if it's a 1 to 4, and I have the larger number on the right side, then I know that my voltage is going to be stepped up by a factor of 4. And if I see that the larger number is on the primary side, then I'm going to divide this number by that. Okay? I don't generally do this calculation like that. Okay, so that's how we can make a larger voltage. Now, we can also go in the other direction. Let's go ahead and step the voltage down. We're going to do a step-down transformer. Well, for a step-down transformer, let's say let's give ourselves a 2 to 1. And let's say this is 60 volts peak to peak. Let's say this is a 2-to-1. Well, what's it going to be? Well, I got 2 times as many turns. Whoa, 2 times as many turns on the input as I have on the output. And so 60 volts peak to peak, I know I'm going to be stepping this voltage down because this side has fewer turns, hence lesser voltage. And so if I have 60 volts peak to peak going into a 2-to-1 transformer, I'm going to divide 60 by 2. So I get 30 volts out. Okay, again, that's not enough. 30 volts what? Peak? 30 volts RMS? No, it's peak to peak because that's what I specified my input as. Okay, so yeah. Any questions thus far? How about we hook this up to the wall? Okay, so right now I have a transformer. Is there a limit to how much you can step up? Not really. So what you have in your wires going across from like behind your house is going to be thousands of volts, 4,000 volts, somewhere around there, I think. It's more efficient to transmit higher voltage. Yeah, I mean, I'm sure there's some practical limit. Like, obviously, you know, as far as a transformer is concerned, there's only so much magnetic field that I can build up, at which point the core will saturate. I won't be able to build up any more. I'm not sure. I don't know what those limitations would be. Okay, so let's go ahead and say we have 120 volts RMS plugged into this input. And, oh, I got to turn my oscilloscope back on. Yeah, once you start looking at changing voltages, man, you really need something to be able to view that. And oscilloscope's your number one tool in this instance. Fortunately, we got the at-home instruments for 211 and 311. I'm testing them out for the last couple of labs for 311, and you'll get them next semester in 311. So we're going to start off the semester with your own oscilloscopes at home, which is really cool. There, that'll work. So I'm probing the output, and in fact, let's go ahead, let's probe. Don't worry about that center tab for now. Let's go ahead and pull up. Here we go. Okay. So it looks like we got something, but it's a bit high. So I'm going to change my vertical. Why is it not updating on the... Oh, There we go. Okay. And I'm going to actually back this off. Okay. So what do we got coming out of this guy? Well, I'm going to go ahead and take a measurement. Okay, I'm going to place this one at the bottom of my waveform, and I'm going to take the other one, and I'm going to place that at the top. Okay, so I am getting, if you look at the delta over here, okay, so this is the measurement on the top cursor. It's at 40 volts, and the bottom cursor is at about minus 40 volts as well. The delta is the difference between the high and the low voltage. So in this case, I'm getting 80 volts. 80 volts what? 80 volts peak to peak. I'm going to write this one down. Okay, 80 volts peak to peak is the same as if I just said 40 volts peak. And if I wanted to talk about RMS, all I have to do is take 40 volts and times that by 1 over root 2, or multiply it by 0.707. They're essentially the same. So let me go ahead and say 0.707 times my peak voltage of 40 volts gives me a root mean square of 28.28 volts. Okay, and I'm writing those down because we're going to actually look at the input to this transformer. I will attempt to do this without blowing myself up. So there's 120 volts coming out of here, so I don't suggest playing with your wall outlets unless you know what you're doing. And let's see. I'm pretty sure. Let me double check my electrical outlet and make sure I'm tapping into the right side. All right, I'm just going to have to guess. Let's see. My oscilloscope is rated to safely do 300 volts RMS. So 120 volts should not be an issue. Make sure that I don't end up shorting this out anywhere. There we are. So all I did was pierce through the heat shrink tubing that I put on there to keep me safe so I don't accidentally touch the thing. And let's look at that input. Okay, so if I go ahead and take another measurement of the peak. All right, what does that say over there? What's my voltage? What's my peak voltage? About 170 volts, right? That's exactly what I expect to get out of my electrical outlets. 170 volts peak, which is 120 volts RMS, which is 340 volts. Look at the delta. Sorry, I should have backed this off a little bit. Look at the delta, 340 volts peak to peak. Okay, so I am getting what I told you guys was coming out of my electrical outlet. That's pretty good. So I'm gonna stop probing that, put the transformer off to the side. Okay, so now I know my input voltage. And we'll just look at the peak voltage. "170 volts peak was my input. 40 volts peak was my output." Okay, 170 volts peak input, 40 volts peak output. Is this a step down or step up? It is a step down transformer because I'm getting less voltage out than I'm putting in. Okay, now can I figure out what my turns ratio is for this transformer? Absolutely. 170 volts peak divided by 40 volts peak. .25. .25 to 1, right? And they have more turns on the primary than the secondary. I know this because the fewer turns, the side with the fewer turns is the lower voltage. So 4.25 to 1. Okay, so I'm going to go ahead and end this here. We learned AC voltage today, and we learned transformers, and I showed you guys on the oscilloscope a few different things, and you guys saw an alternating magnetic field in my compass. Kind of cool. What's a professional outlet fork inserter? That was actually my first cue to my mother. I should stop recording at this point. My first, the first incident that my mom knew there was something weird about me was when I was a child. I took metallic objects to the outlets, and I used to shove them in there. And my mom saw me doing this, and my mom said, you know, my mom was the type that was like, I don't want to have to put little outlet covers over everything. So my mom was just like, I'll let him do it once, he'll get a good shock, and then he'll never do it again. And so I inserted some metallic objects to there. Sure enough, little Eric gets zapped pretty hard, and I kind of crawl away. And then I went back to the outlet later, and I started finding more objects to shove in there because apparently I kind of enjoyed the electricity. And then my mom was really annoyed because she had to start using covers. I lost Zoom here for a minute.